Good morning, everyone. Yeah, I'm Jinyuan, a PhD candidate in the Department of ECE at Duke University. Yeah, today I will present BadEncoder, so backdoor attacks to pre-train the encoders in self-supervised learning. This is a joint work with Yupei and my advisor Neil. A key challenge of the traditional supervised or transfer learning is that they require lots of labeled training data. Self-supervised learning is an emerging machine learning technology that aims to address this challenge. Self-supervised learning only requires lots of unlabeled data, such as unlabeled images or image-text pairs, which we call pre-training dataset. A self-supervised learning pipeline includes two key components. In the first component, we use a pre-training dataset to pre-train an image encoder. In the second component, given some downstream tasks, such as traffic sign recognition, digit classification, and object classification, we can use the image encoder as a feature extractor to build classifiers for these downstream tasks. Next, let's see more details about these two components. SimCR is a popular self-supervised learning algorithm. I will use a toy example to illustrate how SimCR pre-train an image encoder. Suppose we have two unlabeled images. SimCR first uses its data augmentation operation to create two augmented images for each image. Then SimCR uses an image encoder to compute a future vector for each augmented image. The image encoder is updated such that if two augmented images are from the same image, their future vectors have larger cosine similarity. And if two augmented images are from different images, their future vectors have small cosine similarity. Suppose we have some training images of a downstream task. Given an image encoder, we can use it to compute a future vector for each training image. Then we can use future vectors and labels of the training image to train a classifier via standard supervised learning. Given a testing image, we can use the image encoder to compute a future vector for it. Then we use a classifier to predict a label for the future vector. The predicted label is viewed as the final prediction results for the given test input. In our work, we propose BadEncoder, the first backdoor attack to self-supervised learning. So what is a backdoor attack? Roughly speaking, in backdoor attacks, an attacker can inject some backdoor behaviors into a machine learning model, and backdoor behaviors can be activated when the input of the machine learning model contains a backdoor trigger. When the input is an image, the backdoor trigger may look like this. For instance, a white patch. Given backdoor triggers and a clean image encoder as input, our BadEncoder outputs an image encoder with backdoor behaviors. We call it backdoor image encoder. When the backdoor image encoder is used to build classifiers for many downstream tasks, these classifiers simultaneously inherit backdoor behaviors. For instance, when the backdoor image encoder is used to build a classifier for the traffic sign recognition task, the classifier can correctly predict the stop sign. But if a white patch is added, the classifier predicts the speed limit of 60 miles per hour as the attack desires. The behaviors of the classifiers for digit classification and object classification are similar. Our BadEncoder shows that a backdoor image encoder can lead to a single point of failure of AI ecosystem. Next, let's move on to a threat model. We consider two possible attacks. First, the attacker can be an untrusted model provider. The model provider pre-trains an image encoder and crafts a backdoor image encoder. The backdoor image encoder is shared with its customers. The attacker can also be a malicious third party. For instance, a third party may download an image encoder from the internet and then craft a backdoor image encoder. The backdoor image encoder is shared with the customers. To reach the goal, the attacker first selects a downstream task and a class, which we call target downstream task and target class. For instance, they could be traffic sign recognition and speed limit of 60 miles per hour. In our BadEncoder, an attacker can select multiple target downstream tasks and multiple target classes. For simplicity reason, I will focus on single target downstream task and a single target class. An attacker aims to craft a backdoor image encoder to achieve two goals. The first goal is the effectiveness goal, which means that backdoor attacks should be effective. The second goal is the utility goal, which means that we should not sacrifice the utility of image encoder. To perform the attack, we assume the attacker has some unlabeled images, which we call tag dataset. For instance, when the attacker is an untrusted model provider, the attacker can use the pre-training dataset as a tag dataset. When the attacker is a malicious third party, the attacker can use some publicly available dataset as a tag dataset. The attacker also has an image in target class, which we call reference image. For instance, when the target class is a speed limit of 60 miles per hour, the reference image could be an image of 60 miles per hour, as shown in the figure. As we will see soon, this reference image can help achieve effectiveness goal. The key idea of BadEncoder is that we can formulate BadEncoder as an optimization problem. We use effectiveness loss to quantify effectiveness goal, and use utility loss to quantify utility goal. Then we minimize a weighted sum of the two losses to craft a backdoor image encoder from a clean image encoder. However, quantifying those goals faces several challenges. The challenge of quantifying effectiveness goal is that the training process of the target classifier maintains integrity and confidentiality, so the attacker cannot exploit such process when crafting a backdoor image encoder. To address the challenge, we make a backdoor image encoder output similar filter vectors for reference image and any image embedded with backdoor trigger. Therefore, the classifier built upon backdoor image encoder is very likely to predict the same level for reference image and any image embedded with backdoor trigger. When the reference image is correctly predicted as a target class, then the image embedded with backdoor trigger is very likely to be predicted as a target class. Formally, we define the following laws, where DA is a tag dataset and X is an image in the tag dataset. S is cosine similarity. We use cosine similarity because it's used in self-supervised learning. F prime is a backdoor image encoder. E is backdoor trigger, and X plus E is image embedded with backdoor trigger. Xi is reference image. And this is normalization parameter, which is the number of images in the tag dataset. However, L0 alone is insufficient because the reference image may not be predicted as a target class. Therefore, we also make a backdoor image encoder and a clean image encoder output similar filter vectors for reference image. Formally, we define the following laws. S is cosine similarity. F prime is backdoor image encoder. F is clean image encoder, and Xi is reference image. This is our final loss to quantify effectiveness goal, and laminar 1 is a hyperparameter. The challenge of quantifying utility goal is that the attacker does not know which downstream tasks the backdoor image encoder will be used for, so it's very challenging to directly quantify utility goal. To address the challenge, we quantify utility goal using the outputs of the backdoor image encoder. In particular, we make a backdoor image encoder and a clean image encoder output similar filter vectors for images in the tag dataset. Formally, we define the following laws. DA is a tag dataset, and X is an image in the tag dataset. S is cosine similarity. F prime is a backdoor image encoder. F is a clean image encoder. Our final optimization problem is as follows. Where lambda 1 and lambda 2 are two hyperparameters, we can use gradient descent to solve this optimization problem to craft a backdoor image encoder from a clean image encoder. Next, let's see some evaluation results. We use Server 10 as a pre-training dataset and use SimCR, a popular self-supervised learning algorithm, to pre-train encoders on the pre-training dataset. We use GTSRB, SVHN, STL10 as downstream tasks, which respectively represent traffic sign recognition, digit classification, and object classification. We use a fully connected neural network as a classifier. In our attack, we need to specify a tag dataset, reference image, and hyperparameters. In this talk, we use a pre-training dataset as a tag dataset, and we collect one image from the internet as a reference image, and set lambda 1 and lambda 2 to be 1. We also consider other settings, and the details can be found in our paper. We use the attack success rate to evaluate the effectiveness of BadEncoder. Suppose we have some clean test images of the target downstream task. We can add a backdoor trigger to each of them. Then we use a classifier that is built upon backdoor image encoder to predict a label for each image with backdoor trigger. Attack success rate is defined as a fraction of images with backdoor trigger that are predicted as a target class. This table shows that BadEncoder is effective, where the first column is target downstream task selected by the attacker when crafting a backdoor image encoder. As we can see, BadEncoder can achieve very high attack success rate, which means that BadEncoder is effective. We use clean accuracy and backdoor accuracy to evaluate the utility of clean image encoder and backdoor image encoder. Suppose we have some clean test images. We can use a classifier that is built upon clean image encoder to predict a label for each image. Clean accuracy is defined as a fraction of images that are correctly predicted. Similarly, we can use a classifier that is built upon backdoor image encoder to predict a label for each image. And backdoor accuracy is defined as a fraction of images that are correctly predicted. This table shows that BadEncoder maintains utility. The second column is downstream task that we evaluate the utility of clean image encoder and backdoor image encoder. As we can see, backdoor accuracy is similar to clean accuracy, which means that BadEncoder maintains utility. We also evaluate BadEncoder on using a real-world case study. We apply BadEncoder to OpenAI's image encoder, which is pre-trained on 400 mini image text pairs collected from the internet. This pre-training dataset is not publicly available, so the attacker can use the ImageNet dataset as an attack dataset. And similarly, we collect one image from the internet as a reference image and set lambda 1 and lambda 2 to be 1. This table shows our results. We have two observations. First, attack success rate is very high, which means that BadEncoder is effective. Second, backdoor accuracy is similar to clean accuracy, which means that BadEncoder maintains utility. We also generalize existing defenses for backdoor attacks to classifiers to defending against our BadEncoder. We consider empirical defenses and provable defense. For empirical defense, we consider user clearance and MNTD, which are two state-of-the-art methods to detect whether a classifier is backdoored or not. For provable defense, we consider PatchGuard, which can build a classifier with formal security guarantees against backdoor attacks. Due to time constraint, I only show the conclusion here and omit the expanded results. We find that user clearance cannot detect backdoor image encoder, and the detection accuracy of MNTD is close to random guessing. Our results show that PatchGuard provides insufficient robustness guarantees against BadEncoder. In summary, self-supervised learning is vulnerable to backdoor attacks. We find that insecure encoders lead to a single point of failure of AI ecosystem. Existing defenses are insufficient, so we need a secure self-supervised learning algorithm. Thank you for listening. Yeah, I'm happy to take any questions.
All right, so we have time for questions. Please go to the mic, state your name and affiliation.
Hi, thanks for the nice talk. This is Virat from UMass. So what data augmentations did you use for the SimCLR? Did you try strong augmentations, or have you sort of experimented with different augmentations maybe?
What do you see? Can you say it again?
What data augmentations did you use in the SimCLR? Because
You mean like augmentation?
Yeah, augmentations.
Okay, so for in SimCLR, it's data augmentation operation is a combination of a series of operations like random reset crop, Gaussian blur, right, and color jitter and so on, right. So actually we use its original version. Yeah.
I see.
Yeah, you can go ahead.
Thanks for follow-up question. I think most of the original SimCLR augmentations are weak augmentations, weak data augmentations. But have you tried strong augmentations, which have random crop or auto augment based contrastive learning approaches?
Yeah, so you are talking about whether our method can be generalized.
Yeah, exactly. Yeah.
I think So I think by design, actually, BadEncoder does not rely on how the encoder is pre-trained, right? You can see this, how the losses are defined, right? It does not involve the property, right, or some property of the encoder. So I think in our evaluation we use SimCLR, but I think it can be directly applied to many other encoders. But how it will perform, so to be honest, we currently don't know yet.
Okay, cool. Thanks.
Thanks.
Hi, great talk. Yingqi from Purdue. So I can understand why existing defense like neural cleans could not just directly detect the encoder, but if the user actually trains the trailer classifier for their tasks, and they combine this trailer with the encoder, it's essentially just a typical ML model. Then why cannot those defend this whole ML model?
Yeah, thanks for the question. So basically, you are saying we have an encoder, right? It's like a future extractor, and built up on this future extractor.
Yeah, I think for user to use this encoder, they need to build up
classifier, right?
Yeah, classifier, and they combine these two. I think it's still kind of similar to what existing ML model is, and MNTD or neural cleans should be able to detect triggers in this scenario.
Not necessarily, right? As you can see, first, we actually evaluate those defenses, right? We find actually they cannot detect.
Yeah, I think those defenses cannot detect just given the encoder, because there is no classes. But even with the trailer classifier, those scanning methods still cannot detect backdoors.
Yeah, sorry for the confusion. Yeah, so basically, when we, for example, when we apply neural cleans to, basically we generalize the neural cleans to detect whether, our BadEncoder, right? So actually, we apply the neural cleans to a compilation of the encoder and some downstream classifier. So actually, we detect the classifier, not our encoder.
Oh, so even with the classifier, neural cleans still cannot.
Exactly. Yeah.
So can you provide some intuition why neural cleans still cannot? Because that should be the same, kind of similar to the model neural cleans evaluated on.
Yeah, I think for its current version, maybe it cannot be detected because it's maybe tailored to classifier, right? You see how when we use a training data set or a backdoor training data to train a classifier, right? We apply standard supervised learning. But in self-supervised learning, right? We first use an encoder to generate some future vectors and then train a classifier, right? I think maybe it's due to the mechanism difference. But I think it's very interesting to further generalize or some adapt neural cleans somehow. For example, we make modify its loss, right?
Oh, I
that
see.
tailored to encoder. So maybe we can directly detect the encoder rather than the classifier, right? So
Okay.
I think in that way, it may help. Yeah.
Thank you very much.
Hi, thanks for the great talk. Hector from UCSB. My question is kind of similar as a former one. So can you comment a little bit more on how the self-supervised learning backdoor detection is different from the better studied classifier backdoor detections?
So you are talking about the potential difference between detecting bad encoder
Yes.
and
Yes. Do you have
backdoor
any insights
classifier.
on this? Yes.
I think that's a good question. Yeah. So for detecting classifier, right? So I think, for example, a classifier it may have some confidence scores, right? So based on these confidence scores, we make some predictions. Basically, we take the index with the largest confidence score, right? Mm-hmm. So I think when they design those defenses, they basically once the confidence score for the target class is largest, then it will be predicted as a target class, right? So they do not care about the specific value of the confidence scores, right? But you see, when we design our bad encoder, basically we make the encoder have produce specific future vectors, right? But I think in that way, so we need to care about its specific value. So I think that's maybe one difference.
Okay, thank you.
Yeah, thank you.
So I guess that I'm holding you all for lunch, and we're finishing the session. And thanks to the speaker once again. Thank you.
Thank you. Yeah, thank you, Lauren.